This is the last lesson in chapter 2. We're going to talk about the last three objectives. The last three objectives describe two effects you feel every day that are created by mass, describe the mass of objects in grams and kilograms, and then finally use scientific notation, which I actually have a second video to watch about scientific notation. So the first key question is, how is mass described? Now, most of us in our society, we hear the word weight all the time. So when we're talking about a mass of something, it's always a comparison between two things. We look at how much does one thing compare to another thing. So in science, the word mass is the amount of stuff that an object contains. There's two effects that mass has on matter. The first one is you have a weight. Now that weight is actually how much force there is on you because of the Earth's gravity pulling down on you. So many students have a tendency to use the terms mass and weight as if they're the same thing. In our class, mass is something that's just how much stuff that you contain. Weight is something that happens because you have a force on you. So really, in chapter 5, we're going to make this really a lot more important. But in this chapter, we just sort of start out with the idea. But in chapter 5, we're really going to make it clear the difference between mass and weight by actually calculating what those values are. So gravity acts on an object's mass. That's what really happens there. The second effect is what we call inertia. And again, we're going to learn more about this in chapter 5, but you may have learned it in your 8th grade science class. It's the tendency of an object to resist change in motion. Now, what you probably learned in your 8th grade science class was that objects in motion stay in motion and objects at rest stay at rest. And if you think about that, what that means is objects in motion stay in motion. That means objects have a tendency to keep doing what they were doing. That's a resisting change. So if you think about that, an object resists change in motion means it tends to keep doing what it was doing in the past. So if it was at rest, it tends to stay at rest. If it was in motion, it tends to stay in motion. So those are the two effects that mass has on matter. Inertia is really coming from the fact that you have mass. That's what gives you that value or that thing called inertia. We measure mass using the kilogram. That's the standard unit. We talked about that a little bit when we were talking about the metric system. We always use in this class kilograms, meters, and seconds. Those are the base units. So what is a kilogram? Well, if you took exactly 1 liter of water, that's 1 kilogram. So if you see, we have a scale here, and 1 kilogram is exactly equal to 1,000 cubic centimeters. 1,000 cubic centimeters is the same thing as 1 liter of water. You guys are probably familiar with a 2-liter bottle of soda, so just kind of imagine that cut in half. That's going to give you how much 1 kilogram is. Now, you probably aren't used to using kilograms to measure yourself. So the rule of thumb, the way that you can sort of just easily identify how much you might be in kilograms, you take the value of kilograms and multiply by 2.2. So if you take something like a person, and you say that they're 55 kilograms, if you multiply it by 2.2, well, let's just say I multiply it by 2, that would be like 110. So this person is probably 2.2. This is probably 120 pounds. So 120 pounds, that's 55 kilograms. That's just a rough estimate. Again, if you want to take a motorcycle that's 200 kilograms, if you multiply it by 2.2, that will tell you how many pounds it is. So a motorcycle, probably about 440 pounds. A liter of soda, like 1 liter of soda, would be 1 kilogram. So 2 liters of soda would be 2 kilograms. And again, if you want to know how many pounds that is, you multiply by 2.2. So 2 liters of soda be about 4.4 pounds. And then we have a cat there, that's about 5 kilograms. So this kind of gives you an idea of how much a mass is in relation to pounds. Okay, so the very last topic of the whole chapter is scientific notation. Scientific notation is important because it takes really, really, really small numbers and really, really, really big numbers and makes them easier to deal with. So what is scientific notation? Well, we have this number in front called the base. Then we have a power of 10. The base unit is usually written with only one digit in front of the decimal point. So you'll see something like 2.5 times 10 to the third. One thing that's wrong is for you to say something like 25 times 10 to the anything. We usually put one digit decimal point and then whatever needs to go after it. And then we multiply it by something, which makes it equal to what it was before. So really, 2,500 is the same thing as 2.5 times 10 to the third. We're taking 2.5 and multiplying it by 1,000. 2.5 multiplied by 1,000 would just give you 2,500 again. So why do we do this? Well, it's really important when you're talking about something like measuring the mass of the Earth. The mass of the Earth is something like 6 times 10 to the 24th. So when you talk about having to write out 24 zeros, you might make a mistake and only write 23. So it's easier for us to use scientific notation. Same thing with something like really small. That's why we use scientific notation. I have another video which describes using scientific notation. So I'm just going to stop this video now